Every materials has its own direct and coupling coefficient. Therefore, in prior class, we introduced the two direct coefficient, which is L capital Q and L small q. This one is related with thermal conductivity and equals to kappa T. And the L small q is directly equals to electrical conductivity. Okay, so next, we are going to talk about uh, the coupling coefficient, which are L small q, capital Q, and L capital Q, small q. What are them, or uh, which material property correlated with this coupling coefficient? And that would be for the L small q capital Q that were related with, we call the Seebeck coefficient. And L capital Q small q were related with Peltier coefficient. But here probably you will find that this just the Q small q capital Q and capital Q small q. So probably we can introduce to you what is the relationship between them. Due to the Ansaka symmetry on page 49, um, the results actually they are the same. But let me give you like the full story, a brief description why we can consider they are same. We assume we make an assumption that under local equilibrium, thermodynamic equilibrium conditions, and we have the change in heat divided by the total volume equals to temperature times the change in entropy. And sigma dot, which is the rate of entropy production per volume, uh, is like larger or equals to 0. And as we mentioned, as we talking about that, the flux force equation is like this. And we find that we do have a symmetric coupling coefficient. What this means the coupling coefficient here was a symmetric, which means that the change in flux of entity I caused by the driving force Fj is equals to the change in flux of entity J caused by change the driving force I. So this is, if you interpret into coefficient, that would be the coupling coefficient. Or in other words, when you apply a unit of Fj, the changes in flux I, we call the L, the right-handed side is driving force, right? Is the J, and left-handed side is the flux, Lij. And this term actually, you also can explain that in when you apply 1 unit of Fi, the changes in Jj. Then you can write it down L, the driving force, and the flux. So it's Lji. And due to Ansaka symmetry, they are same. The 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 deviation of Ansaka symmetry principle is based on the microscope reversibility for systems near equilibrium condition, which means that it only works on all the driving force, all the systems we're talking about are very close to equilibrium conditions. OK，所以在这里的话，Ansaka symmetry 某种程度上是为了 simplify，了为了简化这个 coupling coefficient 之间的关系，所以它假设就是，在很接近平衡状态的时候，Lij 会等于 Lji。那 Lij 是什么？其实就是当你给它一个单位的 Fj 的力的时候，那它在Ji 这个前面右边是力嘛，然后左边是 flux， 所以是一个单位的 J 的力贡献在I 的 flux 上面，叫 Lij，会等于它们反过来 Lji。那主要因为都是间接的力，都不是直接的力，都是 coupling，所以它假设当这两个力很小的时候，就是所谓的接近平衡状态，某种程度上就告诉你这个力很小的时候，力很接近平衡状态的时候，就跟我们在推导 flux force equation 的时候，我们都假设这个力史上，在 Taylor's series expansion 那里，我们也假设力很小的情况之下，我们可以假设 Lij 等于 Lji。那 that will simplify your calculations in the following slides. So that's back here. So actually, LJQ will be equals to L small q capital Q will be equals to L capital Q small q, right? Based on the Ansaka symmetry. And only works under every the system is near equilibrium conditions. But anyway, the following slides go into proof this Seebeck coefficient as or introduce what is the Seebeck effect and what's the Seebeck coefficient, and also prove that L small q capital Q equals to dou st, or in other words, S and Seebeck coefficient equals to L small q capital Q divided by low t. Okay, so let's and also after we finish this one, then we will move to what's the Peltier effect and what's the Peltier coefficient, and also show you this how to derive these results. So let's move to the Seebeck effect first. In 1822, it's around like 200 years old. Thomas Thomas Seebeck actually he discovered that a compass needle was deflected when the two junctions were maintained at different temperature. What this means, because Seebeck put a magnetic needle under or inside this settings, and what we have a copper on the top and conjugate or connect with this bismuth. And we do have two junctions here, but hit one junctions up. That will lead we do have a temperature difference at two ends or two junctions. So which what this means that they find that as long as this happens, and he find that this compass needles deflected. Okay, so when you and all this description turns out that we induce a temperature difference, but we visualize the diffraction of this magnetic needle, which means that probably there's a magnetic effect, right? It sounds like we do have the interaction between the thermal and the magnetic effect. But he did more experiments. He changed the different types or kinds of materials, and also change the temperature difference, which means that probably uh, different how to change heat up to different temperature to cause we had to have a different temperature difference. And he find that this magnitude of the diffraction, the magnitude of this deflection of this magnetic needle only depending or varied with the type of conducting materials we choose, and also the temperature difference we measured between these two junctions. But it did not depending on the temperature distribution along both these conductors. So it turns out a different combination of these two materials matters. So after further investigations, he found the whole story should be this thermal difference or temperature difference somehow induce a current passing both these materials. And this current induce a magnetic field to cause or lead the needle deflected. So if you think further, actually it's due to we apply the thermal difference and that lead what we have a current. So it's some kind of we call a thermal electrical effect. It's quite famous. Thermal difference induce a current, so it's a thermal electric effect. And actually, how to quantitatively describe this effect? Oh, would be like some kind of if you apply a 1 unit of temperature difference, so if you thermal driving force, then how much current or how much current will be induced. So it's some kind of a relationship between the F capital Q versus the J small q current density. Actually, based on the definition, is quite close to L small q capital Q, right? Because for definition, L small q capital Q actually is when you apply the 1 unit of F capital Q, which is a temperature difference. Then how much the current density, what's the how much that will contribute, how much current density would be, we call it as L small q capital Q, right? Okay. So this is a feedback effect. We apply the temperature difference and which lead the current that will lead or cause a current passing through your materials. So people usually will use this thermoelectrical effect to be a battery to supply or provide the current. Okay, so how to back to the Seebeck coefficient. Seebeck coefficient actually how to measure the Seebeck coefficient, which is the like a material property to describe these materials. So Seebeck coefficient actually is defined as when you apply the temperature gradient and how much electrical potential gradient be generated. So we also put a negative here. So we call it Seebeck coefficient. But how to measure materials Seebeck coefficient is quite easy. We do have like here we have the film here or the bulk materials here. For the film, thin film here, we just put this thin film materials on the top of heater, and the other side is the cooler. And we use this to generate the temperature difference. And in the meantime, we measure how much the electrical potential gradient be generated. Then we have then and put a negative here, so we get the Seebeck coefficient. The same idea, if your materials is bulk, then also you just heat one side up and cool one side down. Then you also can measure the electrical potential gradient, negative electrical potential gradient. Then you can get the Seebeck coefficient. Okay. So if you look carefully, this definition actually is L small q capital Q. This is F capital Q, and this term is related with this because right, but how to derive um their relationship, we will show that in the following slide. But based on the definition, we know that we apply a F capital Q and we do generate a current due to this electrical potential gradient. 所以在这里的话，Seebeck coefficient 事实上就是根据定义的话，就是我给它温差嘛，然后我量它产生电位差。那只要有电位差产生，就会产生电流。所以这也是很经典的所谓的热电材料，因为 thermal 然后 induce 的current，那它常拿来当做电池。 作为一个 power supply。OK，那所以它这个其实就跟我们那时候在讲 L small q capital Q 事实上是有关。至于他们真正详细的等式会在后面会有一页投片，就是跟大家分享他们真正是什么样的关系。但可以预期它一定跟 seedback coefficient 是有关的，因为在定义上是有那么一点关联。And furthermore, regarding to the seedback coefficient, as we mentioned, we do have like materials we call thermoelectrical materials, right? But how to are there any like indicator to um, to quantitatively determine whether these materials are good enough to are good or not to be a thermoelectrical material? And yes, we do have is we call a figure of merit Z equals to the seedback coefficient square of seedback coefficient times the electrical conductivity divided by the thermal conductivity. If you have larger Z, which means that this material is more suitable, have higher performance in thermoelectrical effect. So based on this Z, you know that if this material have higher seedback coefficient, higher electrical conductivity, but lower thermal conductivity, that will for sure will have a highest Z. And this class of material will be suitable to be used in thermoelectric applications. OK，所以在这里的话，大家就可以知道说，如果是你要拿来做热电这个效应的话，也就是透过温差产生电，或者是接下来讲的透过给它电流，然后吸放热的话，那这样这类材料通常我们会用 Z 这个指标来描述，呃，就是热电就能有热电效应的这一类材料。那如果 Z 值越高的话，那它就越适合拿来做热电这个的应用相关的应用。那这样这类材料有什么特性？它有很高的 seedback，它需要有很高的 seedback coefficient，然后它要很导电，但它要会有很低的 thermal conductivity. So based on this, like, this criteria, you will know metal is not suitable. It's not one kind of materials for thermoelectric application, right? Because metal, they do, although they have a higher conductivity, but they also have a higher thermal conductivity. Okay, so in most of case, semiconductor usually is suitable for thermoelectrical applications. Okay, so also not polymer, right? Polymer also have poor or bad electrical conductivity, even though they have a lower thermal conductivity. So it's some kind of balance. So in most of case, people use some semiconductors are best thermoelectrical materials. And so following for real thermoelectric applications, usually people will use P-type or N-type semiconductors materials. And I want to give you an example here, which is people use thermoelectrical materials as to be a power generator, which means that this device serves as a battery. Okay, due to this is a server battery, so provide a current passing this resistance. So this is, don't forget, this is a battery. But here you see that we do have two materials. The first one is we call P-type and N-type, and after we have hotter, we have a cooler at the bottom. So to create a temperature difference. Okay, so due to we have a heater on the top, and the left-handed material belongs to P-type materials. So the major carrier is a hose. So due to this is hotter. This is hotter than this side, right? So due to this thermal energy, that will push the major carrier diffuse along the temperature gradient to the low temperature side to decrease the total free energy. So it's some kind of temperature gradient to drive the major carrier diffuse. And as long as the major carrier, which is a host, diffuse along these directions, then we have the higher electrical potential at the bottom. And the other side is we use the N-type materials. The same idea. We do have a hotter side, which means that the major carrier electrons have higher energy. It tends to go to somewhere with low energy. So the electrons tend to go to this side, go to downward, right? So that will lead the potential at this side is smaller or lower. So based on here, you see have a higher electrical potential and lower electrical potential. So that will lead the current passing through this resistance. So the driving force actually is a temperature gradient to allow the major carrier with higher energy tend to move to downward to the location with lower energy. So this is the whole working mechanism. Okay, so let's do some check here. This is how thermoelectrical materials to be a power generation. But as we talking about that, the Seebeck coefficient actually is defined like this. So my question would be, so for N-type materials, is the Seebeck coefficient is Seebeck coefficient positive or negative? So based on the definition, we can do some kind of check. We just try to draw the temperature as a function of, yeah, sorry, it should be like okay, so temperature should be higher. Okay, so temperature will be higher. Higher is a temperature as a function of location. So temperature at top will be higher because we have hot side here and cold side here. And at the bottom, due to let's say hot side to push the major carrier, which is a electron move to the bottom. So we do have the electrical potential as a function of location will be go lower and higher. And due to here, you do have electrical potential gradient divided by this one and have negative. So this is positive, the slope is positive, then you have negative. So for N-type of material, the Seebeck coefficient is negative. But for P-type of materials, this temperature distribution not the same, right? But the electrical potential gradient will be different because the major carrier, the holes, accumulate at the bottom because be pushed or tend to move to the bottom. So we do have like this. So for let me so for P-type of materials, it will be like this. Sorry. So it's also 5. But we have like because the holes move to the bottom, so we do have the higher electrical potential at the bottom and lower at the top. So let's divide it by this is negative. We have negative, so it's positive. For P-type material, Seebeck coefficient is positive. Okay, so give you a quick summary here. Back to the lesson point. First thing is every material have its own Seebeck coefficient, which means that when you apply a temperature difference or gradient on any one materials, they will generate some electrical potential gradient, and its positive or negative determined on its major carrier. For p-type material, be positive. For n-type material, be negative. And for application, because just only one materials, the electrical potential gradient, the generated electrical potential gradient is tiny. It's difficult to really be a power generator. So in most of the time, when you see a really device, which is a thermoelectric device serving as a power generation, usually they at least have like 100, even 1,000 couples of this kind of PN device，他们至少都会是上百、上千或上万一对这种就是这种组合。然后要记得每个材料它其实都有feedback coefficient，你给它温差，像你先不管这个，你给它这个温差，它一定会产生电位差，只是这个电位差很小，所以常常它都这个电流都非常小，没办法作为电池。所以真的要做 power generation，通常他们都是他们这种就是串联的方式存在，PN 串联的方式存在，所以它才会，然后通常会是，一对就是会有3次、4次、5次方对。那概念就是你可以试想，如果把这里换成 P 的话，它就没办法产生电流了，因为我的电流的这里就会一直在往下，然后这也会往下，然后它们两个就没有产生电位差，那它这里就不会有电流。那如果这里是 N 也是啊，它这是负的往下，所以两个都会是负的，所以它也没办法产生电流。唯一能产生电流的方式就是一个配一个 N，它才有办法产生电位差 for 这个被动元件 resistance， 可以吗？OK，好，then just give you an example. Some materials, like as you know that for applications, usually we use like a 1p type, and we use a couple, right, of PN materials. So some people try to, lots of people investigate whether we can just tuning some dopants and can change one materials from p type to n type, or n type to p type. Okay, so this is a typical example showing multi-wall and carbon nanotube. They just not sorry, they just tune the concentration of carbon nanotube in like this epoxy, then they can tune the feedback coefficient of this material from N type to P type easily, and also with the barrier feedback coefficient. Okay, so lots of people deal with this to try to create like N type and P type in just the easy way would be like through the doping or something like that. And the other is let's move to here. Even though you have some idea for like power generation can be the application for feedback effect. And another also the application, another thermocouple um, also based on the feedback effect. So this is you usually use thermocouple in lab to measure the working temperature in the furnace or in anywhere. Okay, you use the thermocouple to measure the temperature. But what's the working mechanism inside here? So we uh, try to simplify the circuit as this schematic diagram. What's inside this thermocouple would be we have a power meter here, and the environment temperature is T. And this you can see this sensor actually is composed of material A and material B, and the junction is here is a sensing or junction sensing site at this junction. And we use this sensor or this junction to measure the temperature. And this will be environment temperature plus delta T. And this is material A, and material B. So this is the thermocouple. So based on this idea, you know what's the working principle for thermocouple. They do have a potential meter and want to measure want to tell you what's the exactly temperature it is. So it's some kind of the signal we read out would be the electrical potential difference to then you know what's the temperature difference. So some kind of you want to the idea is the relationship between the electrical potential difference and the temperature difference. So I'm going to we want to prove that what's the real relationship between the electrical potential difference and the temperature difference for this thermocouple. So in order to know that, you need to obtain the potential difference measured by this potential meter. So to obtain the potential at terminal 1 and 2 in our experiments, so you can imagine that the idea will be if I can integrate because I need to know the potential difference between 1 and 2, right? So the idea will be, how about if I know the potential difference across here, then across here, then I can know what's the potential difference between 1 and 2, right? So if I can integral the potential along junction to 1, so junction to 1, d phi is a integral the electrical potential. Then I also integral the junction. I also integral the electrical potential from junction to 2. So junction to 2. Then I will get, for this one will be phi 1 minus phi j, right? And for this will be phi 2 minus phi j. So if I got this value and this value, though I use this one to minus this one, then I can get phi 1 minus phi 2, that would be phi AB. So this is the whole idea, right? But so next, I need to write down what's equals to what? Phi 1 minus phi j. But equals to what would be, I hope this value will be related with temperature difference. So at this moment, you need to think about, are there any relationship between the um, electrical potential difference or gradient with temperature gradient or difference? So probably you will come out from your mind will be, we do have, because electrical potential gradient is F small q, and temperature gradient will related with F capital Q, right? So one thing can link them together will be the flux force equation and focus on the current density. When a system do provide two driving force, then you can write this down. The current density equals directly driven by F small q, then L QQ, and indirect driven by F capital Q and L small q capital Q, sum them together. And this would be equals to negative temperature gradient divided by T. And F small q equals to negative electrical potential gradient. And as you know, in order to simplify this, what's the current density doing this inside this electrical circuit? Due to we directly connect to the potential meter, the internal resistance is quite large. So can consider as an open circuit, the current density equals to 0. As long as you equals to 0, then you got the relationship between temperature gradient versus the electrical potential gradient. So you just after arrangement, then you can get this one. and divide it here. So you can, okay, so you can get this relationship. We got the d phi over dt, and at current density equals to 0, negative equals to L small q capital Q L divided by L small q T. As long as you got this relationship between the electrical potential gradient and temperature gradient, so you can take this back. How to do this? Because we want to know the electrical potential difference, so we just move here to right-hand side and take the integral on both sides, and starting from integral, so you have a bottom and upper limit, right? The bottom limit is junction to upper is 1, so, and the bottom actually is dt, right? The temperature at the bottom junction is, sorry, T plus delta T, and upper here is T. And because from integral, you got the electrical potential difference, right? But it's alone inside A material, so we have put the A here. And the rest of part here, just copy, sorry, here, you just copy here. And you move dt to here, so you have the dt divided by t integral. And just have a label because it's for A materials. Okay? And you can just simply integral this, right? So integral this will be log t minus log t plus delta t. Sorry, it's a little bit ugly. And this log, this minus this is actually is log this divided by this, t divided by delta t log. And we also have negative, so invert, sorry, you invert, switch so the bottom to the top because you have negative. So we got here. So that's why we have a log 1 plus delta t divided by t. And as long as we assume, okay, and we assume this is quite small, this x is quite small, then we can do this approximation. Log 1 plus x, when x is quite small, then you can just approximate equals to x. You can ignore the rest of part as long as x is quite small. So you will have copy this term here and button x here. And the second term, like your integral from junction t delta t to t, the same, right? Just substitute. The only difference is just the inside is alone B materials. So I just the same one, but just the rest part are the same. The difference just at the bottom, so it's B materials. So I have this equation minus this equation, so I will have phi 1 minus phi 2. So this minus this one, just copy here. So this is our results. We successfully to get the relationship between the major voltage versus the temperature difference. So if you use this thermocouple to measure the higher temperature, then like expected, you have a larger electrical potential difference. You got higher, larger phi AB. You got, if you have larger delta T, then you can get larger phi AB. Okay, this is first information, which is hope that can convince you. Okay, and the second information here is, if you take it here carefully, and do you remember what's the definition for Seebeck coefficient? Is when you apply the button is when you apply the temperature difference, the electrical potential be generated. So you move this bar, this to the left-handed side is a seebeck coefficient, SAB. So you just put here, take the delta t to a left-handed side, divided by delta t. So you will get this one. And just copy the rest of terms. And SAB is a seebeck coefficient A respect to B. So can be written as SA minus SB. So this is implying that this is SA. And this is SB. This is SA. So now I can know what's the relationship between the seebeck coefficient and coupling coefficient. Seebeck coefficient and coupling coefficient, right? L small q capital Q actually equals to S seebeck coefficient times absolute temperature, and this is low, right? Low ST. So the second result here will be L small q capital Q equals to low ST. Okay, so this is the second information we have inside this example. So the first one is I have convinced you that when you measure the higher temperature will lead the higher electrical potential. You can measure, you can get the higher electrical potential difference. And the second thing is I also show that the coupling coefficient L small q capital Q equals to dou ST is related with electrical conductivity seebeck coefficient times the absolute temperature. Okay, then next will be I just grabbed some different types of thermocouples, different types from KNTJEC. The difference actually means that they compose of different materials, different couples of material. The first one is nickel, chrome, nickel, aluminum. This is copper, nickel, and the suggested major temperature range will be also varied. And I also grabs the figures, which the vertical axis is voltage major for this thermocouple, and the horizontal axis is the temperature window or temperatures at different temperatures. So you also can see like we have to have different types of thermocouples, okay? And if some people wish to measure the temperatures between the 400 to 600, which thermocouple offers the best temperature resolution? I already fixed the temperature gradient I'm interested in because I already targeting that I want to measure the temperature between 400 to 600. So which thermocouple can provide you offer you the best temperature resolution would be the E, right? Because the slope is largest. OK，也就是说，如果当你已经，因为其实如果你要量测，你已经知道你要量测的目标物的温度的时候，某种程度上，其实它跟环境温度的温差已经固定了。那这个时候你要找一个解析度比较好的热电偶，比较适合量测这个温度的热电偶的时候，就要看它的电位差的变化。如果电位差变化比较大的话，就表示你改变一个温度，它在系统上面，它的 readout，它的 millivolt 它会变比较大，所以解析度就会比较好，所以会选这个 slope 比较大的。那某种程度上其实就是 electrical potential gradient 比较大 ，OK 吗？那某种程度上它的 seebeck coefficient 也会比较大。So that will be we expected that will have a higher electrical potential gradient, which also means that we have the higher or larger seebeck coefficient difference. Okay, ma? So what does means? Which means that if you want to have a higher resolution, you hope that we have larger phi AB, right? And also, which means that we have SAB higher or larger. But how can you have a larger SAB, which means that I hope SA minus SB is largest. How to do that? What type of material I should choose for A and B? If I have positive one, or positive negative one, or negative negative one, how can I have largest SAB? Should be one positive, one negative, right? If you have like one positive is 5, the other negative minus 5, so you got 10, right? But if you have 5 minus to positive, which means 5 minus 1 is 4. Or negative, like a minus 5 minus 1 is negative 4. So this also explains why the thermoelectrical device always composed by or composed of one P and one N type materials. OK，所以在这里也解释了为什么，因为如果你想要你的热电就举例是热电好了，就是你希望它的解析度比较好，那某种程度上你在追求就是你希望 phi AB 比较大，那 phi AB 比较大就要 C-band coefficient 比较大，那 C-band coefficient 比较大就表示 SA 减 SB 要比较大，那你要怎么选择？你可以是两个都是正的，那相减完之后当然会比较小，或是两个都是负的，还是要一正一负，对不对？所以这比较一正一负的话，它就会一正一负的话，因为这是 A 减，如果是负的，例如说5减负，那就是10，它就会是最大。这也说明了为什么它的 output 就会是最大的，电位就会是最大的。所以如果它是拿来做电池的，我给它固定的 temperature，它的 electrical potential difference 就会是最大的。所以所有的热电元件的组合跟应用，它 always 是一个 P type 配上一个 N type。因为如果我们刚刚说的，如果是 P type，它 C back 会是正的；N type C back 会是负。OK，OK。So give you a quick summary for C-back coefficient. We have finished that. C-back coefficient defined by when you apply the given a temperature different gradient, how much electrical potential gradient be generated, we call it as a C-back coefficient. Also, don't forget a negative term. After series deviation, we confirm that S C-back coefficient equals to L small q capital Q divided by low t. And in order to measure the correct C-back coefficient of your interest material, don't forget should be an open circuit, which means that you can connect to the voltmeter or potential meter also works. Okay.